Okay, hi guys. This is one of the lectures for the week of February 6th. In class, we'll be doing problems this week, and I'm going to post a few lectures online. So this is, let's see. This is lecture 6 today. So we can write this here. Maybe we can't. Let's see. Okay, yeah, lecture 6. Okay, so today will be about what's in basically chapter 8.3 and 8.4 on some common kind of intuitive ideas for estimators and some notation and just vocabulary for talking about the quality of the estimator. Okay, that's 8.3 and 8.4. So a lot of this is review, and the theory will not be covered in detail, but it was covered extensively already in the last semester. And so to just keep it moving, we're just gonna not do that, but it's all been done actually already. And it's a lot of this is just getting a sense of what the notation means. Okay, so, and this is based on table 8.1, but I do think it helps to really think about what it means. You don't necessarily have to read the whole chapter, just understand what we're talking about. I think this video could do it for you. So there's 4 rows in that table, gives you 4 situations where you want to estimate something. And it gives you some estimators, some real obvious kind of estimators that might be good for those conditions. We'll later see when we build up the theory a little bit that these are in fact very good or the best estimators. Okay, point estimators. Now, point is just means, as opposed to interval estimator, it is a single a formula that returns a single number, not an interval, as an estimate for a single number parameter. Okay, in this case, single number for these examples. Okay, so we're going to see 4 of these. So let's consider the first one is I have y1, yn, a sample, their IID, but the distribution's not given. So let's just write PDF not given. So we can just use say EYI is mu, doesn't mean it's normal, and variance YI equals sigma squared. But I know they all have the same distribution and they're independent, but I don't know what the distribution is. And I'm just using these names, mu and sigma squared, just as shorthands for EYI. Okay, we're going to use a hat over the variable to over the parameter to indicate an estimator. So let's write mu hat will be estimates mu. This is just notation, okay, notation. And we'll say y bar, mu hat equals y bar is a good estimator. We will hold off on that, even that word good, but let's just say is an intuitive, it's in the table, okay, as a common idea for an estimator. We've already actually did this one in this class too, and saw that it was unbiased and that the variance can be made small by taking a big sample. Let's just repeat that now. So E y bar equals mu, and variance y bar equals sigma squared over n. And we have this other thing. Usually we take the square root of this. We call it SD, the standard deviation of y bar, or in the text, they put a sigma symbol. This is not to be confused with this sigma here, but it's just a symbol to mean the standard deviation. And then you put the thing you want the standard deviation of down here. So we'll put the 3 equal signs to mean 3 horizontal lines to mean equal. This is just the same thing defined to be this. And this is just the square root of the variance. So this is just defined to be the square root of the variance of, and it's just sigma over square root of n. So this has 2 good properties. One is it's unbiased, this one. When I try to estimate mu with y bar, I know I have although y bar is random, I have the benefit of knowing that the expected value of y bar is the thing I'm trying to estimate. And then also here, here I know that this can be made small, right? So the variance can be made small. So we talked about that last time, that we want estimators that have a small amount of variance and that are centered in on the parameter they're trying to estimate. Okay, so this is preferable to something like this, even though they both might be unbiased. We prefer the one with the smaller variance. So let's just say this can be, so we see sigma over square root of n goes to 0 as n gets large. So it can be made small by taking enough samples. Okay, so that's our first case. Let's just keep going through. There's 4 of these, and we just want to list these. Later, we'll be showing methods to find different estimators, but for now, we just want to list them. 2, suppose y, now this is a special case of 1. This is just a special case of 1. We could actually skip it and just say you should know this, but it's so important that it's probably worth listing it separately. So say I have y1 to yn are Bernoulli p, and we can let y equal the sum of these. So y is binomial np. And what can we say? What would be a good estimator for p? N is a constant and is known. P is unknown, right? We just think of the data. So we have zeros and ones. So p hat estimates p, and the hat means something estimates the thing under the hat. So p hat equal, let's just say y over n is a good estimator, or is an estimator for p, estimates p. In other words, it's the same as above, really. This is just y bar, right? Y is the sum, and I'm dividing by n. So it's the same as above. This is just a special case when the data is Bernoulli. Okay, well, everything also follows. We just list it separately. So EY over N is just equal to P. So it's unbiased. It's an unbiased estimator. And variance Y over N is just equal to P 1 minus P over N. And if we use our notation as from before, the standard deviation of Y over N is just the square root of the variance. So I can just say the square root of P 1 minus P over N. The book, and often it's nice to replace 1 minus P by Q. If you just see this, then you know Q equals 1 minus P. But you don't really need the new variable name. It's just 1 minus P. Okay, so this is the standard deviation, or sometimes called standard error, especially when it's used for an estimator like this. So so we have what did we say last time? This was unbiased, and we say this will go to 0 also, right? So sigma Y over N goes to 0 as n goes to infinity. So we have a similar case we expected to. It's just a special case, right? It's just a special case of 1. Okay, so again, another unbiased estimator whose variance can go to 0 if I have a large sample. That's it for 1 and 2. Okay, 3. For 3, we have 2 samples. We have x1, and this sort of mimics 1 above, but only for the 2 sample case, x1 to xn, x1 to xn1, and y1 to yn2. And let's just say again, PDFs unknown, distribution unknown. But these are IID. These are IID. We can call and all also, they're all also independent of each other, and all n1 plus n2 samples are independent. Sample, let's say, yeah, variables. Random variables are independent. Reason I don't want to say samples is because we may want to just talk about these as the 2 samples and not each single result as a sample. So we'll just say all the variables are independent. So the samples, this is independent of this, and they're independent inside. They're also IIDs, so we can say EXI equals mu1, variance xi equals sigma squared 1, and EYI equals mu2, and variance yi equals sigma squared 2. We can name them, right? Even if we don't know what they are. PDFs unknown. Okay, well, maybe we want to estimate the difference in the means. Okay, so mu1 minus mu2, we should put a hat over the whole thing. We want an estimator for the distance in the means, okay? So this is just a good estimator would be, and we'll just do it this way again, we'll just say, here's a reasonable intuitive estimator of this difference. And this could be negative, it could be 0. Positive is the difference of the ones in 1, you know, the sample means. So this estimates mu1 minus mu2, and we have E x bar minus y bar equals mu1 minus mu2, variance x bar minus y bar equals sigma 1 squared over n1 plus sigma 2 squared over n2. And the standard error, the square root of the variance, we'll use this notation again. And down here we'll put x bar minus y bar is just equal to the square root of this. Okay, all right. So we have this will also go to 0, right? Each term will go to 0. So again, our estimator, this estimator is unbiased for mu1 minus mu2 and x bar minus y bar, the variance of it, sorry, or the rather the rather the what the hell do we want to say? Rather the the variance of the estimator and or the standard deviation or standard error of x bar minus y bar goes to 0 as n1 goes to 0 and N2 goes to 0. So the samples, if they both get big, it will go to 0. If only one gets big, it won't. And that makes sense. Should make sense. All right. And then 4 is just a special case of 3, and similar to 2, we're just going to do the Bernoulli case. So if we have, say, almost exactly the same x1 to xn1, say IID Bernoulli P1 and Y1 YN2 IID Bernoulli P2, and are all independent as well. Then what would a good estimator be for the difference in the probabilities, P1 minus P2 with the hat, equal to, I will just take it to be X over N1 minus Y over N2. Estimates P1 minus P2, the difference in the probabilities. Here again, X is equal to the sum of the X's, and Y is the sum of the Y's, and these are binomials. Okay, we have E X over N1 minus Y over N2. This is just equal to P1 minus P2, so it's unbiased. And sigma, well, let's do the variance first, maybe. And variance is just equal to, of course, sigma 1 squared. Wait, but we have the special one. So the variance is just equal to here, P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2, or I could use my Q notation if I wanted, P1 Q1 over N1 plus P2 Q2 over N2, and sigma X over N1 minus Y over N2 is equal to the square root of that, right? Okay, yes, very good. Okay, this is it for 8.3. I'm going to stop, and I will make another video for 8.4 on the goodness of the estimators.